This is Introduction to Linear Programming for NR 400. We'll be formulating and solving both graphically and with solver the Bob's modified steer timber problem, which is on the class notes page. So in this problem, there's a farmer has 1,200 acres of pasture land. He's considering planting some of that pasture in trees. The objective is to maximize SEV on the property. There's a couple of other constraints other than the 1,200 acres. He can't spend more than $142,500 in year one. There's an erosion constraint, so whatever he does on the property can't exceed 200 tons per year of erosion. So the trick on formulating problems is, as you're reading through it, you should be looking for certain signals. The main one is, what is the objective? And the second thing you need to be looking for are what variables are the decision variables. In other words, what's going to be manipulated to try to increase the objective function. So in this case, it's pretty clear what the objective is to maximize SEV, and what he's considering doing is making a choice between planting trees on some of the land or leaving some of it in pasture and raising cattle. So when we define the activities and define the units for the activities, we're going to set up the problem in a certain way, and when we set up the constraints for those activities, the units become important, so we need to pay attention to that. So I'm going to first do the labels. So I will call activity 1 steer acres. I'll call activity 2 tree acres. So that means activity 1, if it gets assigned 1 unit, that's 1 acre assigned to steer management or pasture. Activity 2 is tree acres, or it consists of 1 acre assigned to trees in the pasture. Those are my 2 activities. My objective is to max SEV. Since the objective function doesn't have a right-hand side, I sort of put my little reminder that this is a maximization problem here. That allows me to, when I look at the problem, to know what I've put into solver. The first constraint, and this is a constraint that's going to be in all of our problems for this class, is an acreage constraint. And when you're reading through the story, constraints are pretty easy to find because there's things like the farmer cannot exceed an annual budget in year 1. Total erosion of the property cannot exceed 200 tons per acre. And you'll note on this one that I don't say the farmer cannot manage more than 1,200 acres, so some folks sometimes forget the acreage constraint, which is a problem. So the first constraint is acreage constraint. The right-hand side of that is we can't manage more than 1,200 acres total. The other constraint we have is year 1 cost constraint. And the other constraint we have is erosion. So let me change the font on this to be the same size as the others. Okay. So I'll change the labels here, or the text, so that we can see the difference between the stuff I'm entering and the setup for the matrix. All right, so our objective is to maximize SEV. We're going to measure SEV in dollars. Since our activities, the unit is acres, then what we need here is dollars per acre. In other words, we're going to take dollars per acre, multiply it times the number of acres assigned to this activity, and when we do that, we'll end up with total dollars. So if I look up here, the SEV for cattle is 1,000, and the SEV for trees is $900 per acre. Our acreage constraint, the right-hand side we put in is 1,200 acres. this is in acres, the activity is in acres, the right-hand side is in acres, so the units on this should be acres per acre, which is there's 1 acre per acre. But basically the way to think about it is when we're looking at different answers, the solver is going to try putting acres into this. For every acre it puts into this, we want to multiply that times 1 and subtract that from our available acres. Year 1 cost is also a less than or equal to constraint. The budget we have is $142,500. And this is in dollars. So the right-hand side of the year 1 cost constraint is in dollars. The columns are in acres. So we need this to be dollars per acre, so that we take dollars per acre, this coefficient, multiply it times an answer in acres, and end up with total dollars. First year costs for steer are $75. First year cost for trees is $150. And there's a year 1 cost constraint. Erosion is also a less than or equal to constraint. The total right-hand side available, our budget for erosion is 200 tons per year. And I have a choice here. I'm going to enter in as tons, but as soon as I enter in as tons, it's going to have implications for a conversion I have to do in the matrix. So less than or equal to 200 tons. This unit is in tons. These activities are in acres. So this cell has to be tons per acre. If you happen to remember that there's 2,000 pounds in an acre, then raising trees causes 200 pounds per acre per year of erosion. If we have to convert that to tons, 200 pounds is 1/10 of a ton. So we put 0.1 in here. And raising steer causes 400 pounds, which is twice this much. So that's 20% of a ton. One thing to note is that in a LP, you have to have either a greater than or equal to constraint, an equal to constraint, or a less than or equal to constraint. But it may make sense to you that we would have wanted just an equal to constraint here, except for that. Okay. So if we were to formulate the problem this way, we'd probably get an answer. And it would make sense that if these are the only 2 activities we're going to consider, that we may want to put it in as equal to constraint. Because if we don't, if we put less than or equal to, it may not assign all the acres. My bias is to give linear programming as much flexibility as possible, and then if it gives you an answer that you don't like, then you change it. In other words, it'd be interesting to know that we could actually make more money by not allocating all the acres. In the end, we may have to put in another activity to reflect the fact that we'll do something different on those acres. So now we've formulated the problem. And this format's called the detached coefficient matrix. We'll look at the equations in a second. So how do we solve this problem?